Welcome to The Explainer. Today, we're going to pull back the curtain on the hidden logic that powers our entire digital world. Okay, so think about this for a second. You hit send on an email, and it travels from New York to Tokyo in what, the blink of an eye? It feels like magic, but it's not. And today, we're going to follow the incredible journey your data takes to make that happen. So here's the first big thing to understand. The internet isn't one giant single network. It's actually an internetwork. Basically, millions of completely separate networks all connected together. So the real challenge is, how does your email reliably find its way across all those different networks to a single device among billions? Well, the answer is something called the network layer, or layer 3 if you want to get technical. And honestly, the best way to think about it is as the internet's own global postal service. It doesn't care about the physical cables or fiber optics. Its only job is to handle the addressing and the routing to get your data from point A to point B. Now, just like that postal service, before any package can be sent, it needs a destination address, right? On the internet, it's exactly the same. Your data needs a kind of digital passport to get around. And that passport is the IP, or Internet Protocol address. Every single device connected to the internet, your laptop, your phone, your smart fridge, gets a unique one. It's a digital home address that ensures a packet of data finds the exact right computer out of billions. Now, these addresses have a bit of a history. We started with a system called IPv4, which gave us about 4.3 billion addresses. Seemed like a lot at the time, right? Well, spoiler alert, it wasn't nearly enough. That's why we had to invent IPv6. It's way bigger, it's more efficient, and it has security built right in from the ground up. Okay, so let's get back to our email. It's been broken down into these little digital envelopes we call packets. Each one is stamped with that Tokyo IP address, and now it's ready to hit the road. The real heroes of this trip are devices called routers. You can seriously think of them as these super fast, super smart postal sorting offices. They don't care what's inside the packet. Their one and only job is to look at the destination address and say, okay, you need to go that way, and send it along. And this journey isn't a direct flight. It's more like a series of incredibly fast hops. First, the packet goes from your computer to your home router. That router sends it to your internet service provider. From there, it's jumping between these massive routers, maybe going under an ocean through a cable, crossing a continent, just passed from one network to the next until it finally arrives in Tokyo. But what happens if a packet gets lost? Stuck in a loop, bouncing between a couple of routers forever? That would clog up the whole system. Well, to prevent that, every packet has this brilliant little built-in self-destruct timer called time to live, or TTL. A packet might start its journey with a TTL value of, say, 128. Every single time it passes through a router, every hop, that number ticks down by 127, 126. If it ever hits 0, the next router to get it simply discards it. Poof, its journey is over, no lost packet circling forever. So our packet is hopping along, its TTL is ticking down, everything seems great. But then it could hit a new kind of roadblock. See, some paths on the internet have very strict size limits. So what happens when our digital package is just too big for the road ahead? This is the problem. Every network link has something called a maximum transfer unit, or MTU. Think of it like the height limit for a bridge. If our packet is 4,000 bytes, but the next network it has to cross has an MTU of only 1,500 bytes, well, it's just not going to fit. The solution is a really clever process called fragmentation. The router that's on the edge of that smaller network basically acts like a slicer. It'll just chop up the oversized packet into smaller pieces that can fit through. So check this out. The first piece, or fragment, gets created. It gets a unique ID number. Think of it like the tracking number for an order that comes in multiple boxes. It also has a little flag that's turned on, which is basically a message saying, hey, destination, more pieces are coming after me. Then, the next piece shows up. It's got the exact same ID number, so the receiving computer knows it belongs to the same original packet. It also has something called an offset, which just tells it where this piece fits in the puzzle. And notice that more fragments flag is still on. And finally, the last piece arrives. Same ID, of course, but this time, the more fragments flag is turned off. That's the signal. It tells the computer in Tokyo, that's all of them. You have all the pieces now. And it can use those ID numbers and offsets to perfectly reassemble the original message. So our little packet made it. It got chopped up, sent across the world, and reassembled perfectly. It's amazing. But this entire system, built on these IP addresses, was heading straight for a cliff, a catastrophic failure. See, the original system, IPv4, only allowed for about 4.3 billion unique addresses. Back in the 80s, that seemed like an impossibly large number, more than we could ever possibly need. But then came, well, everything. The explosion of PCs, smartphones, servers, smart devices. And by the early 2010s, we had completely exhausted the supply. We ran out, flat out. No more new addresses to give away. The internet was running out of real estate. The long-term solution is IPv6. It expands the address space to, well, look at that number. It's 340 undecillion. That number is so astronomically huge, we could give an IP address to every single atom on the surface of the Earth and still have plenty left over. We are not going to run out again. But you can't just flip a switch on the entire internet overnight. So the transition is this gradual process. We use clever strategies like dual stack, which lets devices speak both languages, old and new, and tunneling, where we literally wrap a new IPv6 packet inside an old IPv4 packet to help it cross outdated networks. It's a slow but steady migration. So after following this packet all the way across the world, what's the big takeaway here? Why does any of this matter? It's this. The network layer is the absolute unsung hero of the internet. It's the invisible engine. This simple, elegant set of rules for addressing, routing, and even fragmentation is what makes everything else we do online possible. It brings order to the chaos and connects billions of us every single second. And that leaves us with a fascinating final thought. For decades, the internet's growth was actually limited by this lack of addresses. Now, with the virtually limitless real estate of IPv6, the question is no longer if we can connect something, but what will we connect next? The foundation for a truly massively connected world has only just been laid.